On this week's show, with electrics, hybrids, and hydrogen nipping at its heels, our panel discusses the future of the piston engine, and you just may be surprised. Coming up next on Autoline This Week. Underwriting for Autoline This Week has been provided by Borg Warner. And now, here's your host, John McElroy.
I want to thank you all for joining us on Autoline this week. The discussion is going to be all about alternative powertrains. You know, even though everyone says that we're on the verge of all buying electric cars or maybe even buying fuel cells that run on hydrogen, maybe the piston engine has got more life left in it than you might think. I've got three people in to talk about that today, including Matthew Riley. He's the CEO of a company called Nautilus Engineering. Isak Lofgren is the CEO of a company called Achates Engineering. And David Johnson is the CEO of Achates Power, and want to thank all three of you for coming on the show today. So I'll throw it out to all of you. It's a jump ball. Is there life left in the internal combustion engine?
Of course.
So much you wouldn't believe it.
Why so?
Well, what we're doing at Achates Power is we've developed an opposed piston engine that is a leapfrog in efficiency versus conventional engines. And so that really reinvigorates the marketplace. What the world needs now more than anything else is a fuel-efficient engine to solve our challenges in oil and emissions and so forth, but they also need to be very, very cost-effective. Cars are already getting expensive enough, and when you add very expensive batteries, that really reduces their ability to penetrate in the marketplace. Okay,
we'll get into more details of what this opposed piston engine is. Matthew, you said, of course the piston engine's got life left in it. Why?
Well, eventually we're probably going to wind up running on nothing but hydrogen at that point, because you're looking for the best emissions possible. But at this point, with low temperature combustion technology, which is what we research and develop, our technology gives you the ability to do a very low temperature combustion and have virtually no NOx emissions whatsoever. But we've also went a step further. We're able to control and maintain better emissions. Hydrocarbons and COs are extraordinarily low because of the technology that we're working on. We're able to do something currently that no one else is able to do. And our technology is not only adaptive to just about any type of piston engine available, it's also an assimilation technology. It will go in and work with any technology to help it be better than what it was before and increase its thermal efficiency, increase the quality of the product, and it also increases longevity. Obviously, higher temperatures tend to do more damage to an engine over a period of time. Lower temperatures do a lot less damage, and it also increases your longevity. You're also looking at a thermal efficiency of up over 52% currently.
Which is high, and that's higher than normal engines. And let's get into the details of that in just a minute, but I want to hear Isak. Why do you think there's still life left in the piston engine?
Well, basically on this, the piston engine has been around for about 100 years, so it's a long gone development. And also in the car industry, you have this cost efficiency, which is a high driver. So every time you're going to introduce new technology, you gotta see for the performance and the emissions, but you also need cost efficiency. And for that, as the piston engine is very well worked in, we see the potential of actually still enhancing by little step by little step. It's a heavy work, but the gains when you do that small everyday, day-to-day work on a piston engine is actually more cost efficient when if you're going to translate to a completely different technology. And you mentioned this is important with the hydrogen engine, and there are, for example, the two different types of hydrogen engines today. Either you take a conventional combustion engine and make it fit for being fueled on hydrogen gas, or you have those fuel cell technology. But then I would say in the 20 to 30 year time, it's pretty obvious that as soon as you can solve the problems you're having today with the combustion engine, piston engine being driven on hydrogen, that's a much more cost-efficient package. And you already have the entire production capability around the piston engine, which you don't have on fuel cells, for example.
You do now. Okay, David told us that he's got an opposed piston engine. Matthew's talked about low temperature combustion. What do you do at Kasi Engineering?
We do high efficient boosting system for IC combustion engine downsizing. So it's a package where we put in a lot of mild hybrid functionality, waste heat recovery, and e-boosting, which is electrical turbocharger boosting. So we spool up the turbocharger to get better performance, but at a very low cost. Then you also have those like stop-start functionalities and kinetic energy recovery. All that has been packed into one single unit, which is made up by the standard turbocharger and the standard alternator on the car. So we actually just add one new hardware component to the system, but you gain a lot of new functionalities, which together with a piston engine makes it take a leap forward, a great leap in terms of fuel efficiency and performance.
Okay, I'm very interested in what Isak and Matthew are saying here. Matthew, you pick it up from here. You're saying that maybe fuel cells are not the best way to use hydrogen. Maybe we can use the internal combustion engine with hydrogen?
We can, and if you've had a chance to look at our technology and what it is, we don't have direct injection. We don't use port fuel injection. We have a throttle body injection. We've went back to an older technology, but increased the pressure a little bit. We're able to do a full homogeneous mix outside of the combustion chamber, which no one else can do, to drag into the combustion chamber and then cause detonation. It's actually a flameless ignition. Everything at once ignites instead of a flame propagation that gases will expand the area and force the piston down.
So what you're saying is, doesn't matter if it's gasoline as a fuel or
Correct.
diesel as a fuel or hydrogen as a fuel.
Correct. We're more efficient, more powerful. Doing a homogeneous charge instead of just a flame propagation, you have a much higher in-cylinder pressure than what you do with conventional flame propagation. Flame propagation is a higher temperature, and you're also expanding gas as it goes out of the exhaust. With HCCI, you're a much lower temperature, you have more combustible, everything's combusted at once. It's complete combustion in the cylinder at once, versus a flame propagation where you have to do stratified ignition, stratified injection. All that's eliminated now. It reduces your costs by about 30% over the conventional engine platform now, which means all you're doing, you're not changing the entire engine, you're only changing the cylinder head and the piston. Everything else can stay the same. You're still going to use a NOx sensor, O2 sensor, throttle position sensor. But this engine doesn't require throttle losses like conventional engines do, because your butterfly either stays open when the key's on, closed when the key's off. When it's open, the fuel injector is allowed to inject fuel once this determines the crank is spinning. When the crank's spinning, it ignites the fuel by combusting it, compressing it, boom, your combustion occurs. We have a primary and secondary combustion because to give you an idea, there's been several $100 million spent by all the multitude of different automotive makers. They've spent all this money trying to research and develop HCCI and have not been able to get it to run in idle all the way up to 8,000, 9,000 RPMs. Our technology allows it to do it at idle, do cold starting, and run 8,000, 9,000, even as high as 10,000 RPMs.
And you're absolutely right, because I've had different automakers talk to me about their efforts in HCCI, and I haven't heard from any of them in years. But David, let's go to your engine design a minute, talk about that, because what I find intriguing is you're talking an engine that's, what, half the size and half the parts in it? Explain what you're doing here with your Achates Power engine.
Gladly. So picture a 6-cylinder engine with inline 6-cylinder with a cylinder head on top. Take that cylinder head off and just throw it away. We don't need it anymore. You cut that cylinder block in half, cut that crankshaft in half, flip one on top of the other. Now you have the kind of engine we work with. It's an opposed piston engine. So we've got 2 pistons in one bore, no cylinder head gasket, no valves, no valve train, no camshafts. All those parts go away.
i.e. a lot smaller, a lot lighter, a lot
so
less
it's
costly.
smaller, it's lighter, and because of those 2 pistons in one bore, it's dramatically more efficient. And whether we're talking hydrogen or compressed natural gas or ethanol, methanol, gasoline, diesel, biodiesel, biofuels, all these things can burn in this engine, and we burn them more cleanly and efficiently than any other engine. And I think, it's a beautiful thing, the panel you put together, because basically all these technologies can be complementary, right? Yeah. We need better boosting. Kinetic energy recovery, hybrid vehicles, all these things are possible in combination. But our technology, what we bring to that, is this much more fundamentally efficient engine with lower cost. And that's what's going to drive the volume in the marketplace. And that's where our technology is going to win versus, things that are very, very expensive, which a lot of people are considering and look good from a technology perspective. But when they go out to the consumer, like you look at electric vehicles in the marketplace today, sales are down. Sales are down because they're too expensive.
Yeah, no, that's a key thing that you're talking about here, is not just coming up with something that's more efficient, but cheaper at the same time.
Right,
That's a killer combination.
Right.
The beautiful thing about Achates Power's technology, our patents allow for us to use our technology on their engines and advance them to another level as well. They have a beautiful technology. I've followed that work for years, but being able to have a primary and secondary piston source within a single cylinder also gives you an enormous amount of capabilities for HCCI and low temperature combustion, which means their engine can get another level of high quality, clean emissions, and another level of performance that other ones won't be able to.
Mm-hmm. Isak, what I'm intrigued about yours is everybody has a turbocharger these days, it seems to be, and yet you're talking about new efficiencies in boosting engines, i.e. turbocharging or supercharging them, if I understand, and I'm not an engineer.
No, you're completely right.
So what are you doing differently? What are you bringing new to the party, as they say?
Conventional turbocharging is controlled today by wastegate control, meaning that at a certain amount of exhaust gas power available, you have to open the wastegate, letting mass flow and exhaust gas flow out, bypassing the turbine.
So you're wasting energy when you have to bypass that.
Exactly, and you do that because that's the only way to control the speed of the turbocharger and control the boost pressure. If you don't do that, you will ultimately blow up your engine. So it's a good thing. Saab Automobile was kind of first in the market with series production turbochargers in the early 80s, I believe. And with what we do today is when we connect the turbocharger through traction drive system to the alternator of the car, we actually, instead of wasting and opening wastegate, we break out that waste heat energy back to the alternator and the electrical power system of the car. So we control the speed of the turbocharger with electric machine instead of opening a wastegate.
So you're generating electricity with that waste energy?
We generate electricity, and there's no actual need for bigger batteries in the system, because the electric machine we're using, it's the ordinary alternator of the car. So what we're actually doing is that at highway driving, for example, we use the waste heat energy to drive the alternator, which is the one producing the electric power for all the electric consumers in the car, the stereo, the AC, all that. Today, that is powered by belt from the crankshaft. So when you do this, straight away on a high driving steady state scenario, you take away about 4.5%, which is a fuel saving. And it's also when you can combine that with start-stop technology and electrical super capability, it quite fast turns out that all those hybrid technologies today, they consume electric power that has to be refilled at a certain stage. Our system today, we can go in, start-stop, and do braking, vehicle recovery in city driving. But then if you deplete the battery by e-boosting or performancing too much, when you go out highway driving, we actually get that energy back to the system quite fast.
Very interesting. Yeah. So Matthew, now you got to run me through yours. You've talked about HCCI, which, if I've got this right, homogeneous charge compression ignition. So compression ignition is like a diesel, right? Mm-hmm. You don't need a spark plug. You just compress that fuel until it explodes.
Correct.
What's the homogeneous part of it?
The homogeneous part of it is where you bring in the exhaust gas, your EGR. You do use a linear EGR valve to recycle that exhaust gas back into the intake so it suffocates any kind of flame possibility. Our technology gives you a 30%, 25 to 30% fuel efficiency increase in the engine because you're using less fuel. Conventional engines, for instance, they're doing a 14.7 roughly to 1 air-fuel ratio. HCCI engines, or what we're capable of doing, which no one else is HCI, homogeneous compression ignition. That technology allows you to do 31-to-1 air-fuel ratio.
So you're using very little fuel.
Very little fuel. You're actually vaporizing the fuel from the injector on a throttle body, which means you no longer need the electricity for the multitude of direct injectors, the port fuel injectors or direct injectors, which most people are having to do either port fuel and direct to try and do HCCI. They haven't been very successful at it. They spend an enormous amount of money trying to do it and they haven't got there. Our technology allows us to go in and assist any type of piston or rotary technology and help them to, it's an assimilation technology. It allows you to go in and help them create better efficiency, more power, and better longevity. Lower temperature burns or ignitions are, I shouldn't say burn, lower temperature ignitions are the wave of the future because you don't have the NOx emissions created.
Now explain that a little bit because so the audience understands. When you have a low temperature ignition,
you don't create,
most of the emissions go away, right?
A great deal of the emissions go away. NOx being the main emission that you're concerned with. The ozone layer is what gets damaged the worst by NOx emissions. Hydrocarbons and COs, you can control them with catalytic converters or primary secondary catalytic converter. More than likely just by a primary. There's very efficient catalytic converters that are being developed right now to work very well on HCCI engines or HCI engines. No one else has been able to do an HCI engine because that's just homogeneous compression ignition instead of trying to charge it. The opportunities in this field are incredible right at this moment. Everyone's always been trying to develop a SI engine and turn it into a homogeneous charge compression ignition engine. That was the wrong approach. They should have just left out the whole SI altogether and tried to develop an HCI engine, which is what we've done. We have a primary, secondary. If you ignite HCCI before top dead center, it literally will destroy an engine. It'll blow a head gasket, twist a piston in the cylinder, bend a rod, break a crank. It's like hydrolocking an engine. For anybody that's ever gotten water into the engine through the intake in a flood or something, it bends rods, twists cylinders, things of this nature. Well, it's that much more pressure within the cylinder. If you can harness that energy that's being dispersed in that fashion, you now can produce more power to the crank. And that's what we've done.
Now I get it all. You all have pretty interesting technologies and new approaches of design. David, I know you've been at it at Achates for what, at least a decade now?
Yeah.
I think you've put
12 years.
$100 million of research into the Achates engine. Unbelievable. When might we see this in production?
They're coming soon. So we're working with customers around the world right now to take our technology out of our lab and bring it into production. Most of those I don't get to talk about still to this day, unfortunately, but they're coming. But we've got really good work with
But you're talking about big manufacturers.
Yeah, we're talking about big manufacturers. So as an example, we're working with, in a publicly announced program with Cummins, we work with on a military project that for our friends down the road here in Michigan. And that's going very, very well. We've had excellent success. Our engine's in their labs, running on their stand and producing excellent results. So we have similar projects with all the companies we know and love from around the world, but I don't get to talk about them, but they're coming. Engine programs take from start to finish on the order of 5 years, and we're in the midst of that now. So you can see in the next few years our products on the
So maybe 2020 we might.
Yeah, no, I think it's very relevant. It's very relevant for both commercial vehicles, for greenhouse gas 1 and 2 regulations, and also for CAFE 2025 here in the U.S. And, around the world, everybody wants better fuel efficiency, and no one wants to pay for it. And so that's where we've got a very excellent solution that really the leading automakers, guys that you have on here all the time, are very, very interested in, but they won't tell you about it, but they are.
Okay, Isak, how long have you been working on your development?
It's an interesting story. We've been working, actually we founded the company in Sweden 2007, started working full-time in the company.
And now you mentioned this before, this is at the old Saab company?
Yeah, it is. Our first collaboration was started in 2009 together with Saab Automobile and one of the top tier universities in Sweden. So we were during 1.5 years, this was also during the crisis, so we were up running and we did prototyping, we did engine testing, we did optimization of those engines based on testing and simulation, and it was then planned for a concept vehicle for Saab, which was supposed to go out on a Frankfurt saloon, where they ultimately failed because we all know what happened. And so we had this tough meeting in the beginning, I think it was 2011 springtime, with the CIO of Saab Powertrain and the staff, where we actually had to pull out our company because we had a great technology, and so we had this friendly splitting at that time. And from that, we started to work with a Swedish Tier 1 manufacturer towards commercial vehicles and be doing that. And now, since 2 years, we're up and running again with a major OEM manufacturer.
Whose name you cannot tell us.
No, it's pretty the same, NDA agreements and all that. So we've been doing simulation and packaging studies, and they are really interested. But we, compared to this, we're a startup company. So we're now in this GAMIC Venture Cup competition, and we need to secure funding here on the US market, and also to be able to team up with Tier 1 manufacturers, because they are actually the ones that can be the market channels for this complete product that we're bringing. We're capable of taking production for those new parts in it, and also, of course, the engineering services and licensing agreements. But in the end of the day, if we're going to bring this five-year to market plan, which is fully realistic, but it doesn't go faster than that. And you also have to respect those structures in this automotive business, that the OEMs that are really interested in the technology today, but they need established large Tier 1 to be the one taking the handling cost, the purchasing structures, all that.
Well, hopefully we've got some Tier 1s watching the show right now. Maybe you'll get a phone
You're
call.
welcome.
The good news is that these technologies don't require a new manufacturing facility, right?
No.
The engines we make,
That's exactly.
all these can be made in existing plants. So unlike, as you talk about hybrid vehicles, batteries, and fuel cells, these all require substantial investments in new manufacturing plants.
Yeah. So Matthew, I want to hear your story now. How long have you guys been at it? When might we see your HCCI system in production?
You'll probably see it in the next 3 to 5 years in production. I might add that 3 major universities in the state of Kansas have signed on board with us. We've signed contracts with them. I also might add that we are meeting with General Motors, Ford, Chrysler, Toyota, and Honda, and Hyundai. Our technology is leapfrogging rapidly. Because we're able to do low combustion temperatures, the NOx emissions are now meeting 2025 standards today. That is what everybody's been chasing after, and I'm honored to be working and seeing these guys here in this conversation, because their technologies assist us.
Yeah, I would say that's
gain tremendous.
Interesting.
Well, this is interesting. So Isaac and Matthew, you guys would just license your technology to major manufacturers. Dave, you mentioned that you're working with Cummins along with the U.S. Army.
But it's also a licensing.
A licensing. So none of you are going to manufacture this, but you're going to sell your ideas to those who will.
We actually have the opportunity of both, but I would say it's more probability to get, because again, then if we're going to get to market, it's a better model.
Our view of it is we want to create more jobs, but at the same time, it doesn't make any sense to my investors, which I might add, I've had a phenomenal investment group. We're extraordinarily well funded. We haven't had to get any public funding whatsoever. The thing that really shocks me is that you have a multitude of manufacturers that have wonderful people working in these jobs currently. Why would I want to take those jobs away or remove them? I'd like to do everything I can to ensure and secure their jobs. And I believe that's an end goal for probably all of us, is to increase their quality of life.
Good. So let's just run through. I'm curious what kind of fuel efficiency improvements you might see each one. Dave, Achates, what are you guys saying?
So our engine in the lab today demonstrates 20% better fuel efficiency than leading production diesel engines. So you take the most efficient engine in the marketplace, and our engine tests 20% better. We've got a roadmap that takes it to 30% better, and we now just this spring started a project to do gasoline version of our engine. It's a $9 million award from the U.S. Department of Energy, and that will allow us to run basically on any fuel, and compared to gasoline engines like downsized, turbocharged direct injection, we're expecting a 50% improvement in fuel efficiency.
Wow. Okay, Isak, what kind of fuel efficiency do you think?
We have measured on the new European driving cycle. So we have figures for the US cycle as well, but I can't manage that. But I would say on the new European driving cycle, and also with the reference engine, this 2-liter gasoline engine, turbocharged, which was the reference base engine we worked with during the Saab era. Based on that, and when we added our system, we got in between 13 to 18% fuel efficient, and that's a combination of all those functionalities. The e-boosting functionality, which means that you can change the end gear, like down speeding, downsizing your engine a little bit. You get the waste heat recovery, which is this 4.5% on the highway driving type of the cycle. You get the start-stop capability, which is around 3.5% for those cycles. And then you get the kinetic braking recovery. So every time you idle or you break down.
Okay, now 30 seconds, Matthew.
I might add that easily we can hit 25, probably 35% increase. We haven't begun to optimize our technology yet. We're hoping to work with some of the other people in the industry to make it much more proficient.
So I know we can't add these together, but combination-wise, no, I mean add them together, but I'm not saying, 50% plus 35%.
We're down to
We're going to go over 100%. But very interesting. The piston engine still has a lot of life left into it. David, Matthew, Isak, want to thank you for your time today. Very interesting conversation. I know we only skimmed the surface because you guys are way deeper into this, but I hope you enjoyed this as much as I did.
Underwriting for Autoline this week has been provided by Borg Warner.